Hi again. So this video will talk about limits at infinity. So, you can also have functions and you can, try to understand what will happen when x gets positively very large or when x gets negatively very large. Okay. So this is when we talk about limits at infinity. So let's say we have some function given. Then the limits when x goes to positive infinity of f and the limit when x goes to negative infinity of f are called limits at infinity. Limits of f at infinity, of course, we can have plus infinity or minus infinity. These will also tell the end behavior of their graphs. Okay, so these two limits, when you know these two limits, then you also know that how do the end of the graph of the function f look like. Okay, so I will give examples, but let's start first writing this like limit x goes to infinity of f is the output values of f get close to, let's say this is L. L can be infinity as well. We will come to that too. Get close to L. So L doesn't have to be finite here, but we will see with examples. Get close to L if x gets arbitrarily positively large. So let's just do some examples. For instance, let's say f of x equals 1 over x, something we know, right? If we look at the graph of this function, we know that the graph looks like this. So this is the positive infinity direction. This is the negative infinity direction, right? So as you see, 1 over x, it gets smaller and smaller. Like if you take x equals 1000, then f of 1000 will be this, which is 0.001. Or if you take x to be 1 million, then you are going to have something even smaller, right? So it's going to get smaller and smaller, smaller and smaller, and almost like zero. So we say the limit x goes to infinity, because we can choose bigger x's than these. We can choose 1 billion, 1 trillion, 1 quadrillion. We can go bigger and bigger. And then in that case, the function 1 over x will be getting smaller and smaller values. As you see, it's getting closer and closer to zero. So we say the limit is zero, and you can see from this graph also. Okay. What else? Okay, now let me also write the negative infinity case. So we say when limit x goes to minus infinity of the function is equal to L. As I say again, L can be finite or even infinite again. So, but let's say something, some result. then this means when x gets negatively arbitrarily large, then the values of f is approaching to L. Okay, so as I said, this can be infinity also, but just like the previous example, if we take 1 over x, then if we remember the graph y, x, well, the graph looks like this, also looks like this. I didn't draw it the other time, but I could have drawn anyway. But it's getting closer and closer to this line here. This is the negative infinity direction, this is the plus infinity direction. But as you see, when x gets negatively arbitrarily large, this function is getting closer and closer to zero, like zero is here. So it's getting to this, close to this line, that line, on that line, the values of f, the y values are zero. So it's getting closer and closer to zero, okay? So the limit of 1 over x, when x goes to minus infinity, is zero, okay? But there are also other functions. For instance, let's say find x goes to minus infinity of, let's say, e to the x function. Let's remember the graph. The exponential function, it has a graph like this. It grows exponentially fast, but then it gets closer and closer to zero as x goes to minus infinity. So we can say, as you see, the larger and larger negative values of x, the outputs will be getting smaller and smaller. They are getting close to the x-axis line, which is when y is zero. So this limit is zero. But what about the limit of this function when x goes to positive infinity? So, well, this graph will just go like, this way, okay? It's getting bigger and bigger. If you give some large number for x and take the exponent of, take the exponential function of that very large x, you are going to get even a larger number. So you are going to find, as you see, it's going in the positive infinity direction here. It's going in the positive infinity direction. So this limit is infinity. So as you see, when you look at the limits at infinity, you can find some finite numbers, but on the other end, you can find some infinity limit, okay? So these are all possibilities. Or let's think about another example, which is, let's say, well, log function. Well, log function is only defined for positive numbers, so we can only think about the positive infinity limit. So again, let's remember the graph. It's the mirror image of e to the x function. It's going to look like this. This is ln of x function. This is the infinity direction. This is the infinity. This is the minus infinity. This is the minus infinity. So as you see, if you give bigger and bigger values for x, this graph is going to positive infinity. It's not turning back. It's getting bigger and bigger. If you take the ln of a very large number, you are going to get maybe smaller but still a large number. You can make x bigger and bigger, so then you are going to get bigger and bigger numbers. So limit of ln of x when x gets very large is also arbitrarily positively very large. Okay. Another example, let's say x cubed. So let's look at the function x cubed. when x gets positively very large and negatively very large. So again, it all comes down to remembering those graphs we have sketched earlier back in the very beginning. So y, x, so x cubed, remember the graph, it's going something like this. This is the positive infinity, this is the negative infinity direction for x. This is the negative infinity direction for y, positive infinity direction for y. As you see, when x gets positively very large, what happens with the values of y? It's also getting positively very large. So this is equal to positive infinity. What about the limit at negative infinity? So let's say you start with something negative and then you make it more negative. You can make it more negative and more. As you see, it's getting to more and more negative numbers. So the limit at the negative infinity of x cubed is equal to minus infinity. Okay, now the last thing about these things is horizontal asymptotes. So we say that the line y equals L is called a horizontal asymptote of f if either limit x goes to plus infinity is L or x goes to minus infinity is L. So either end point or either end behavior at the plus infinity or minus infinity is equal to some finite number. Here L is finite number. Then we call this a horizontal asymptote. If L is an infinity also, then there is no horizontal asymptote. So an example here, we actually did some of them, like let's say 1 over x function. If you remember the graph, 1 over x function looks like this. This is x, this is y, plus infinity, minus infinity, minus infinity, plus infinity. As you see, the limit as x goes to minus infinity of 1 over x is getting smaller and smaller, 0. So y equals 0 is a horizontal line. Or you can also look at as x goes to positive infinity, as you see, the graph is also getting smaller and smaller and getting closer and closer to 0. So y equals 0 is a horizontal asymptote for 1 over x function. Or you can think about this earlier example. Let's say f of x equals e to the x. We just said that x goes to minus infinity is 0. Remember the graph? The graph is something like this. This is y, this is x. This x is also y equals 0 line. Okay, this y is x equals 0 because this is 0, 0 here. Okay, this point origin. And since this is the case, even though the positive infinity limit is something positive infinity, we don't care about that. Just one side of like minus infinity is some finite number. So we say y equals 0 is a horizontal asymptote for e to the x. Okay. Uh, Another example is tangent. So when you look at the graph of tangent function, what you will see is something like this. Remember, tangent is sine x over cosine x. So when cosine gets 0, tangent will get undefined. However, you will see, and when does cosine get 0? So that means x equals pi over 2 or 3 pi over 2 or goes like this, or minus pi over 2 minus 3 pi over 2. It will be undefined. But if you draw this, so you will see asymptotes like these. Okay, these are going to be vertical asymptotes, but there is not going to be any horizontal asymptotes. So, okay, so you will see graphs like these. Okay, so x equals 2k plus 1 over 2 pi is a vertical asymptote. Well, for the horizontal asymptote, well, we don't have that anyway. But I'm going to come down to horizontal asymptote just by looking at the inverse function of this. Okay, so if we think about the inverse of tangent, which is arctangent, you can either write this way or this way. So remember, this is, then we are going to take the graph of tangent and take the mirror image with respect to y equals x. So the arctangent graph is going to look like this. But remember, we have to have a one-to-one function also. So the arctangent function's graph, so we are just going to take one period of that graph to have a one-to-one function. So we are going to have a graph like this. So this is pi over 2. This is minus pi over 2. Okay. And this is inverse of tangent or arctangent function. So this is plus infinity. This is minus infinity. And these dashed lines are, as you see, horizontal asymptotes. So y equals pi over 2. Okay, maybe I should just write. When we look at the limit as x goes to minus infinity of arctangent, as you see, it is getting closer and closer to pi over 2. Well, minus pi over 2. So y equals minus pi over 2 is a horizontal asymptote. And in a similar way, if we look at the limit at the positive infinity of arctangent, then we will see pi over 2. And then, when x gets bigger and bigger, arctangent will get closer and closer to pi over 2. So the limit of arctangent when x gets positively very large is pi over 2. So similarly, this is also a horizontal asymptote. So sometimes you can have more than one horizontal asymptote for some functions. So if you have seen machine learning or deep learning, there is also activation functions like which have different horizontal asymptotes. But anyway, so okay, this is what I want to say about limits at infinity and horizontal asymptotes. So we should know these things. Okay, maybe I should do one more example. Right, let's say find when x goes to infinity the limit of 2x squared plus 4x minus 1 over x cubed minus 7x plus, let's say, 5. Now, how are we going to find the limit of this? Now, in these kinds of stuff, we factor the highest degree term. So the highest degree term, okay, we factor the highest degree terms on the top and on the bottom. So the numerator and the denominator. By top, I mean numerator. By bottom, I mean denominator. Why do I factor the highest degree terms? Because when x gets very, very large, positively or negatively, the highest degree terms are going to dominate the top and the bottom. So x squared is going to grow faster than 4x or other stuff. Or x cubed on the bottom is going to grow faster than the other stuff. So we factor those terms. So let's see what happens then. We are going to have x squared on the top. Oops. And x cubed on the bottom. Factoring them means I divide the top by x squared. Then I have 2 here, 4 over x, and minus 1 over x squared. So minus 1 over x squared. So I divide everything by x squared and multiply. That's what I mean by factoring. And on the bottom, factoring x cubed is take x cubed and then divide everything by x cubed. So 1 minus 7 over x squared plus 5 over x cubed. And then remember the limit laws we had. Just you can write it this way. So I'm writing down everything, but you can write this thing faster, of course. So we will see what. First of all, there is a simplification for x squared and x cubed. So that's going to be limit x goes to infinity of 1 over x. And then what about stuff on the fraction here? Well, constant functions 2 and 1, they are just going to be 2 and 1. What happens to 4 over x when x gets very large? Remember the 1 over x function? When x gets very large, that's going to be 0. Or what about 1 over x squared? When x gets very large, that's going to be also very small, 0. And then 7 over x squared, also, it's going to go to 0. And 5 over x cubed, when x gets very large, also will be 0. Okay? Now, I have 1 over x. When x gets very large, that's going to be 0, right? And then 2 over 1, that's 2. Well, the final result is 2. Okay, and remember 1 over x function again, like 1 over x function looks like this. This is the x-axis, y-axis, and x getting positively very large. So when the function is getting smaller and smaller, 0. Okay, the function's output values are getting smaller and smaller, 0. So that's why we have 0 there. So that's the last example I want to solve. And next thing I want to talk about is probably will be continued.